All right, let's take a look at some of the specifications for your shell in Program 4. Um, to start, your shell needs to be able to be called one of two ways. Either with no arguments, as we saw in the last video. In that case, your program will read its commands from standard in, meaning someone can just type into your shell. If it encounters an end to file or some command causes it to exit, specifically the exit built-in command, then it will stop reading, of course. Also, when reading from standard in, just before it gets the input, it should print a string like this to standard error. If you want to make your shell prompt a little fancier, that's fine, but it should be clear that it is a shell prompt in some way. And in particular, you want your prompt to end in a space so that the user's command that they type in doesn't run up against the prompt. The way that the test cases work, though, rather than providing input to standard in, is to provide input via a script file. So when your script is, or when your shell is called with an argument, one command line argument, it should open that file. There might be an error opening the file, in which case you should report the error and exit. And then read commands one line at a time from that file until it reaches end of file, or maybe runs a command like exit, for example. When you're reading from a script file, the big difference, other than where the input comes from, is you shouldn't print a prompt. Whichever way, whether you're reading from standard in or reading from a script, your program should do the following. Read a line from the input, either standard in or the script. If there's end of file, you exit with status 0. That was success. You finished running the script, or the user didn't have any more commands for you. If there was some other kind of error reading the line, you should report an error message. Once you have that line, that might be as a C++ string object, that might be as a C string, a character array, you should call parse command on the C string. If you got a C++ string, you can use the C_str member function to call the to convert that into a C string, which you can then pass into parse command. Parse command will return a pointer to a command structure. You'll need to inspect that command structure, look at its argument 0, which will be the name of the command, and either execute one of the built-in commands if it matches, or if it doesn't match any of those built-in commands, fork and execute an external program. That'll be similar to what you did in Program 3 with a few additions, or in Lab 3 with a few additions. And then finally, call free command to free the memory that parse command returned. Again, parse command, you don't need to implement yourself. That's provided for you. Only if you're doing the bonus do you need to do anything with that. So the parse command function takes a C string argument, command line to be parsed, returns a pointer to a struct command, which, as we saw in the last video, has several members. Args, an array of pointers to C strings, terminated by a null pointer, args0 being the command name, and then args1 being the first command line argument, args2, and so on. The nice thing about this array is it is exactly the form that we need to pass to the exec functions. In particular, we're going to use execvp, which we'll talk about in a minute. It also has an optional input and output redirection, which will be null if we weren't doing those kinds of redirections. If the command line was blank, the command struct that was returned will have no arguments and no command name, meaning args0 will be null. Your program should handle this by doing nothing. If I just press enter, or press space and enter, there's no command, no arguments, your shell should just not do anything and read the next line. But that does mean you will explicitly have to check for null before you start looking at the contents of arg0 to see if it was cd or setenv or exit. You also must call free command, otherwise you'll have a memory leak, and we will be checking for those. So the part that you've kind of already implemented are external commands. I'll talk about those in a moment. Uh, Actually, it's probably easiest to implement external commands first because you already have a big part of the implementation that you need in Lab 3. Also because most of the test cases involve external commands in some way or another. Even the test cases that are about testing the cd command or the setenv command will still use external commands to print messages, for example, to verify that cd or setenv did what it was supposed to do. So if you haven't implemented external commands, pretty much all of the test cases will fail. But before I talk about that, I did want to at least mention the built-in commands. cd changes to a directory. There is a system called chadir. You could look at the man page for it, but it's very simple. It takes a string, a C string. It changes the current working directory of the current process, that'll be your shell, to that directory, and then returns 0 on success, negative on failure. You will need to check the return status of chadir to make sure there wasn't a problem. We saw that in the last video when we looked at test 18, which tries to do a chadir to an incorrect directory. If you have an error in a built-in command, you should not terminate the program, but instead report the error and then go on to parse the next line. That way, that's much more useful for an interactive shell where I might type in a command that has an error in it, but I don't want that to end my entire session. I just want to know about the error so I can fix it up. cd without any arguments should change to the user's home directory. There is a library function called getenv. You pass it the name of an environment variable as a C string, in this case home. It will look up that value, return it, and if there was an error, it will return null. So you will have to handle both of those cases. If you get env home, change to that directory. If it's not null, if it is null, then report an error message. Don't change directories, but again, also don't terminate the program. For all of these library functions and system calls, chadir, getenv, and so on, you will need to look at the manual page to see how they work. And also, in particular, pay attention in the manual page to the section on errors. What is the return status when there is an error? For getenv, it will return null. For chadir, it will return a negative number, and so on. And what are the different kinds of errors it can produce. When you encounter such an error, then you should use p-error or maybe stir error to print an error message. We'll see a little bit more about that in a minute. Setenv, I mentioned in the last video, sets an environment variable. There is a setenv library function. It takes, let's take a look, takes a few arguments. We have the name of the environment variable, so that might be home in all caps, for example. We have the value we want to set it to, so that might be some directory you want to use instead of your regular home directory. And an overwrite parameter, which specifies if that environment variable already exists, should we overwrite it, you should always pass 1 here. We do want to overwrite environment variables. There is a related command described in the same man page called unsetenv, which removes an environment variable. As I mentioned, you should look at the return value to see that setenv returns 0 on success or -1 on error, sets error no appropriately. And here are a list of things that error no could be set to. Unsetenv, again, returns 0 on success, -1 on error. Okay. So the last external command, or internal command rather, is exit. You call exit however many arguments you give. The exit command ignores. It simply calls the exit library function with the parameter 0 to exit with status 0. So that one will be a particularly simple one to implement. Also, remember if the shell didn't contain a command name at all, if I only type spaces or if I just press enter, the shell should ignore it. So those are the special cases. The general case, if the zeroth argument of if the zeroth argument of the command, so command arrow arg square bracket 0, was anything other than cd set env exit or null, then you should treat that as an external command. You'll want to return, so you will already have that parsed by parse command into the list of arguments, starting with command as argument 0, and then any further arguments terminated with a null pointer. If you provided an input redirection, then there will be a member in readir set to non-null, and likewise for an output redirection. If you left these off, the square brackets here indicate that they're optional, then those will be passed as null. And of course, you should handle that and not try to open those files. So to create an external command, very similar to lab 3, I'll point out a few differences here. So you call fork. Fork could return 0, indicating I'm the child, positive, indicating I'm the parent, or negative, indicating there was an error. If there was an error, you should handle that by printing a message. Again, not terminating the shell. If otherwise, we're dealing with either the child or the parent process. So looking at the child process first, in lab 3, you got an input redirect, an output redirection, and you handled that by opening that file with open, not fopen, because and not the C++ ifstream open, because we want a file descriptor number. We use pt2 to move that to the standard out file descriptor, which is file descriptor 1. And then we called exec. So a few differences. Output redirection will be more or less the same. You want to do write only. You also need to add the flags to create a new file or truncate existing files. If you watched the lab 3 video, then you saw what flags we needed to do that. For an output redirection, you do need to specify that optional or that third mode parameter. So that was 0666, for example. If you were given an input redirection, then you should open that file, which you'll need to open with the read-only flag. You don't need to specify a mode. You don't need to specify any other flags in that case. Again, open could have failed. Dupe2 could have failed, so you need to check those. So this is going to be a total of potentially 2 calls to open and 2 calls to dupe2, because you could have both an input and an output redirection. So here I would recommend what you currently have in lab 3 always opens the file. Wrap that inside an if. If the command arrow in readir is not null, then do that stuff. And then you'll have a similar if for output redirection. Your output redirection is what you already have. Input redirection will be similar with a few differences. The other difference, besides needing the read-only flag and not needing the mode, is when you dupe to the input file, you should dupe that to the file descriptor for standard input, which is file descriptor 0. So standard input, file descriptor 0, standard output, file descriptor 1. To execute the process, you'll call execvp. That's different from execve. It's a little bit simpler to use, actually. The two big differences are execvp doesn't take an argument for the environment. So you could just eliminate that argument altogether. If you don't pass an environment with a function like execvp that doesn't take one, then your child process will inherit the environment from the parent, which is what we want anyway. The other difference is if the first argument, or the 0th argument, the name of the command, does not contain a slash in it, then it will be looked up in the path. That's one of those environment variables, which lists the directories that execvp and related functions should search for. That will be very useful because you don't want to have to type /bin/ls or /user/bin/tr, for example. You want to just be able to run the command with only the name. Execvp does that lookup for you. In the parent process, called waitPID, in your lab 3, you used wait. If you wanted to use wait here, that would be okay, but that will make it a fair amount more difficult to handle background processes if you want to do the bonus. waitPID is very similar to wait. The difference is, for one thing, you specify the process ID. Well, if we're in the parent, that means fork returned the child's process ID, so we know what it is we need to wait for. The other thing is we can pass in some options, which say what to do when certain kinds of other behaviors happen. Also, what to do if there is no child process or the child process hasn't exited yet. You definitely don't want to do w-no-hang here because you do want to wait for that child process to exit. W-untraced, W-continued, you don't necessarily need, but you could use. Those affect some things that we're not testing for. What happens when you press Control-Z and what happens when you continue a child that you stopped with Control-Z. Finally, in the parent process, we want to potentially print a message standard error about what happened. If the child exited normally, don't print a message. So that would be this case. It exited normally, so I don't print a message. If I have something that exits with a non-zero status, the command itself hopefully will print its own message explaining why it failed, but then my shell should print something like command returned 2. 2 here is the exit status. In your lab 3, all you did with the exit status was check to see if it was non-zero. Here, you'll have to actually get the value, maybe store it in a variable, pass it to printf, so on. Or fprintf rather, because you're printing standard error. If the child was killed by a signal rather than exiting normally, so let me run cat, ./cat. This is, by the way, another potential kind of error you should handle. I did exec in the child after I forked. Execvp failed because that program doesn't exist. The child exited, and the parent process reported the exit status of the child. But what I was wanting to show you, I'll run this command cat. It reads from standard input if I don't specify any files on the command line, writes everything I typed to standard output. So, okay. If I press Control-C, that will terminate cat, and my program, my shell, should print what happened. Command terminated rather than returned. And as far as the name of the signal, wrong screen. As far as the name of the signal, you can get that from stir signal. How do you figure out which signal it was? Well, just like in lab 3, you used w if exited, w exit status. There's likewise w if signaled and w term sig. So read the man page on wait or waitPID for more information about that. Now, one thing you probably didn't even notice here, but it is important. When I press Control-Z to terminate cat, that did not terminate my shell. If I didn't do something special to handle that, it would have. So you're going to need to use the signal system call to handle at least sigint. that is the interrupt signal. So you call signal, you pass it the interrupt signal, sigint, and you pass it a handler. Now that handler could be a pointer to a function. You can read more about that um, in the slides on exceptional control flow and signal, also in the textbook chapter. So we could have passed a pointer to a function, but we could also pass sig underscore ign to ignore the signal. So we ignore the signal in the parent process, and then after the child process is terminated, we call signal again to reset it to the default, meaning for the handler we pass in sig underscore DFL. We have to be careful that we do this in the parent, only in the parent process. We don't want to do this before we fork, because if we do, the child process will also have the interrupt signal ignored. And we want Control-C to stop the programs that we're running, just not our shell. So you can do that after the fork, just before you call wait. So when you're about to wait for the child process, first ignore interrupts, then do the wait, and then you can restore the interrupt handler. So once you've made those changes to your code from Lab 3, you have the implementation for external commands. I just wanted to mention a few more general things, and then in the next video I'll talk a little bit about how to get started. So you can write either in C or C++. You're welcome to use any version of the standard. You should edit the make file to set the correct flag. So if you want to do the most recent version of C, C11, you have this. If you want to do C++ 17, you can do this, and so on. I believe in the make file right now, it's set up for C99 for C and C++ 11 for C++. If you want to use newer library functions, for example, you can update those. You'll also notice it passes this underscore or this -d underscore GNU underscore source. This defines a macro GNU source, and the reason we do that is that many of the commands we'd want, or many of the functions we'd want to use, such as source signal, are not necessarily part of the standard. They're not part of the C standard anyway. So we can define that to enable those features. Your program should compile with -w_all. If you don't change that in the make file, you already do that. It should be possible to compile and run your program on your virtual machine. We'll be testing on my virtual machine, the grader's virtual machines, which are set up identically to yours. But do be careful about that if you initially build your program on another machine. At the very least, make sure when you put it on your virtual machine, when you do make clean and make, that it does compile with no errors. Every system call and library function that might return an error, you have to handle that error. With one exception, which is functions that print that are exclusively for printing things to standard output or standard error. You don't need to look for errors in. The reason being, if you did have an error calling printf, how are you going to even report that error message? Printf didn't work, it's probably not going to work the next time. But everything else, when you read from the file, however you do that, that could produce an error. When you call the open system call, when you call the fork system call, when you call the exec system call, when you call the chadir system call, all of those things could report errors. You must handle all of those. Unless your program terminates with an error, And that would be one of the few kinds of errors that would actually make your shell exit. For example, not being able to open the script file. But in any other case, your program should free all the memory that it allocates. For the most part, that means every call you make to parse command should have a matching call to free command on the same pointer. And only one call to free command, not multiple. So you just need to make sure you handle that in your loop. If you do any other memory allocation with malloc or with new and C++, you also have to free those in the appropriate way. But probably you won't need to do any of those, except perhaps if you're implementing the bonus. You shouldn't have buffer overflows. You shouldn't have other undefined behavior. We will run your program under valgrind to test it for those. When you're executing an external command, you should use the functions we've specified. It is okay to use wait instead of wait PID, but you should be using execvp to do the path lookup. You should be doing fork. In particular, there are some library functions that will take a command and do the fork and exec and everything else that's necessary themselves. System is one of those. POSIX spawn is another. You should not use those functions. Of course, you could try implementing a shell like that. It would probably work, but we will deduct points because you're missing a big part of the point of the assignment, which is to get more practice in using fork, exec, and so on. Redirections should happen in the child process, not in the parent process. That's important because if you were to do them in the parent process, or if you were to do them before forking, that would mean they would affect all subsequent commands, not just the one that it was provided on. When you're handling redirection, you should use open, not one of the higher level functions, but the lowest level open system call, followed by pt2, as we talked about. Other than those things, that you shouldn't use system or POSIX spawn, that your redirection should use open. Other than that, you can use any of the library functions you want. So any of the C, C++, either standard library functions or even the GNU extensions that are specifically only on Linux or only on GNU systems. You may not link in other libraries. So you're not allowed to link in a regular expression library. You shouldn't need to anyway. There's no use for regular expressions here, but just don't do it. Meaning, on your linker command line, you shouldn't add any -Ls. If you don't do that and you don't include any third-party header files, you should be fine. Output and input redirection should work appropriately. Output redirection should create a new file. There's an option to open for that, ocreat, or truncate an existing file, otrunc. Input redirection should not do either of those things. We don't want to truncate a input file before we even start reading from it, and we also don't want redirecting from with input a non-existing file to create that file. We want it to just fail. And your shell should not produce any output other than the prompt, which should go to standard error messages, which should go to standard error, and the report, as we saw when running an external command, on whether that command exited with a non-zero exit status or terminated because of the signal. Other than those things, all of which should go to standard error, your shell should not produce any output itself. That will all happen in the external programs. If you want to do a little bit of that for testing purposes as you're debugging your program, that's okay, but you should definitely remove those before running the tests. Any output your shell produces to standard out will cause all of the test cases to fail because your shell's output when running the appropriate commands will no longer match the output of those commands. It will have extra stuff in it. Likewise, if you print anything to standard error other than in these cases, it will cause some of the tests to fail because they check that you don't write anything to standard error. Also, the prompt should only happen when you're reading from standard in. If you're reading from a file, you shouldn't print the prompt. if you did, that would cause many of the test cases to fail. As far as error handling goes, you can take a look at this section of the assignment, but in general, you want to produce a two-part error message with the context, what your program was doing that caused the error, and the cause of the error, the situation that caused that to be an error. This first part will be something that you construct. Here, I'm plugging in the name of a command, but there are other ways to do that. Here, I'm plugging in the name of a directory. The second part, it comes from the error no variable. And in particular, you can use p_error. That will print an error message along with a prefix that you supply. So the prefix would be this part before the colon. And it will print that to standard error, exactly what you want. The problem with p_error is its first argument is just a C string. So I would have some difficulty plugging in something like this. I could do it, but it would take some work. So the other thing you could use is stir error. All that does is take the error no, which you pass into stir error, convert it to a string like this, and return the string. And then you can use your message along with whatever variables you need to plug in, and the thing you got from stir error, and output those using printf, for example, or cerr. The nice thing about that is it lets you plug stuff in without having to explicitly join together C strings and so on, which is a little bit on the annoying side. There's a list here of at least some of the library functions and system calls that you are likely to use, and the error messages, all of these could theoretically produce an error. If you call malloc yourself or calloc, that could return an error. You do need to handle that. For each of these functions, you'll want to look in the man page to see how they report an error. Usually, for functions that return an integer, they'll return -1 on an error. For functions that return a pointer, like a C string, for example, then they will usually return null. But there are exceptions. In particular, standard I/O functions like fopen, actually fopen and fclose are probably okay, but fgetS, for example, report errors in a little bit different way. So make sure you check the manual pages. And again, to repeat, your error messages should go to standard error, not standard out. If you're writing in C++, that's cerr. I talked about the test cases in the last video, so I'm not going to go into too much detail there. Just do take a look here about the error messages that you might get. If you run a test, you will get one of these 3 error messages if it didn't pass. So you could read here to see what it's about. The error message will list the file that it saved containing your output or your errors. Out here means standard out, error means standard error, and the expected output file. So you'll want to take a look at those files, compare them, see what the difference is. That might give you a clue as to what went wrong. And again, we don't test the exact contents of the error message, but we do test whether there was an error message or not, and that should be correct according to that expected file. You will need documentation, as in the previous assignment, as in program 1, meaning the author, list of contents, so all of the files that that are in what you're uploading. And remember that what you upload should be a tar or a zip file with everything needed to build your program. Information on how to compile and how to run your program. That could be as simple as run make, type /shell to begin. Implementation notes. Here you should describe and justify any design decisions that you made in implementing the shell. So if you put your external commands into a function, do that. If you didn't put them into a function and you just have one big if else to handle all the possible kinds of commands, describe that there. How do you determine whether a command is a built-in? probably that'll be something like strcomp, strcmp for string compare. But there are other ways to do it. If you're doing C++, you could make a C++ string and compare it with equals equals. Did you do any helper functions for error handling or any other reasons? There should be at least something here. There are all kinds of places when developing your shell where you'll have options on how you do things, and you should describe why you took the options you did. Limitations of your shell. A lot of people in the last assignment, or in rather program 1, the last assignment that had a documentation requirement like this, said, either left this out or said there are no limitations. In this program, there are definitely at least some limitations. So at the very least, you should describe the ones that are there because of parser.c, which is that it supports a maximum of 30 arguments. That is a limitation of your shell. It should be listed. But also, if you used the standard I/O functions to do your input, fgetis, for example, to read from either standard in or the script file, and you did that into a buffer, that buffer has a certain length. That's the maximum length of command line you support. The assignment specifies that should be at least 512 bytes if you do have such a limitation, but also that should be described here in the limitation section. Also, any failing error test cases, any memory errors you noticed, and so on, you should describe those here. Also, if there's anything you found that you followed the specifications, you do exactly what it says, you pass all the test cases, but this is something I really wish my shell did, but it doesn't do. For example, pressing the up arrow to scroll back through previous commands. Your shell isn't likely to support that. If you want to mention that under limitations, you're welcome to. References, you should describe any discussion you had with anyone else about the design of your program. You should not be sharing code with anyone else, but maybe you talked to someone and they said, oh, well, I found it was much easier to use wait instead of wait PID. Or when I called do2, I got this weird error, but it turns out I was doing this wrong. So check to see if you were doing that. If you had those kinds of conversations with anyone other than myself or the TAs, then describe them here. If you want to include myself and the TAs as well, you're welcome to. If you use code snippets from anywhere, Stack Overflow, one of the manual pages, I'm told that in, I think it's section 8.3 of the textbook, there is an example shell, much simpler than what you have to implement. It won't get you very far in this assignment. But if you want to use any code like that, describe what you used, explain how it works in your own words. You're not allowed to use code in this class without understanding it. You should be able to say what it's doing. But you can, if you can do that, you can use this external code. Now, in general, any borrowed code like that should be a very, very small part of your program. For example, if you looked at man wait PID and you looked at the example section and you thought, oh, some of this will be good for handling exit statuses versus terminating programs. That's fine. You're free to use it. However, if your entire program is just made up of copying and pasting things from other places, then you are not doing the programming assignment right, and you will not get a very high score. And again, you may not share code with other students at all. If you get things from sites like Stack Overflow, that's okay. Also, you should not be posting questions about the assignment on Stack Overflow, asking people to write the code for you. But if you do find there a solution to a question someone else has already asked, feel free to use that. Finally, you'll make a zip file containing everything. So that will be, I have some extra stuff here, but that will be at the very least all the provided files with any changes you made to them. You are allowed to change the provided files however you want. Your make file should still include -w all. Parser.c you probably won't need to change unless you do the bonus. Shell.c is going to be your own implementation. That might be shell.cpp or shell.cc. Shell.h is provided. You are allowed to change it. You probably won't need to unless you're implementing your code in multiple files. Run test is provided. You shouldn't need to change. The test directory is provided. You won't need to change. But all of those things should be in your submitted tar file, as well as that README that I just mentioned. So you can make a tar, you can make a zip file. As far as grading, it's similar to program 1. So that's going to be based on the test cases that you pass for 50% of the grade. Some for compiling without any warnings, so you'll lose a few points for every warning. 15 points for having appropriate error handling for every system call and library function that might fail, and those error messages being in the appropriate format. Have both the context, what the program did that caused the error, and the cause, that is, what error no says about why the error happened. File not found, for example. So you will need to have those. Every library function that you call that is missing those, you'll have points deducted for. Or if your error messages aren't in the right form, if you only print the error that comes from error no and not the context, you'll lose some points there. 10 points for the documentation. That is specifically that README file. You should have all the appropriate sections. It should be readable. It shouldn't be missing anything, and so on. And then 10 points for code style, which also includes things like comments. But beyond comments, variable names, formatting. If everything is indented to the leftmost column, then I'm not going to be happy with that. You should have it indented appropriately, of course. Function parameters, if you're writing program, if you're adding your own functions, and you probably will be, they shouldn't have unused parameters or that kind of things. It should be what it needs to be for this program. And up to 15 bonus points for a few things related to background commands, which I'll talk about in a minute. So there is a hint section. Be sure to take a look at that. It describes how to handle things like parsing or figuring out your command line arguments to tell how your shell was run. Hint about how to read from the file. Ideally, you don't want to have to write your input loop twice. In both cases, you're reading something. It's just in one case you're reading from standard in. In the other case, you're reading from a file that was specified on the command line that you opened. Either way, you can use the same library functions for reading from those. There are a couple of ways to do that, depending on whether you're doing C or C++. If you notice that your shell's prompt doesn't appear, there is a system call, or rather a library function that you want to do to tell the standard IO library to flush it, or if you're in C++, a different thing. Usually, or rather I should say, often output is line buffered, meaning things don't actually get sent with the right system call to the terminal until a complete line has finished. And when you're printing your prompt won't end in a new line because you want the user's command to appear right after the prompt, meaning you will need to do probably some kind of flush in between. And then a little bit about calling open. So the bonus is to implement background commands. Background commands are indicated with an ampersand at the end. You will have to modify the parser to handle those. You'll probably also have to modify the command struct to specify or to have a flag, a boolean or an integer or something like that, indicating that it is a background command. Now, I will point out parser.c is written in C. If you were to rename it parser.cc or cpp and compile it as C++, you may get errors. So if you are doing the bonus, you will probably have to write at least a little bit of C code in the parser, if nothing else. But this doesn't have to be that complicated. You can, for example, let the parser do its thing that it already does, and then check the last argument, the one just before the null pointer, and if that is an ampersand by itself, replace it with a null pointer so it's no longer an argument, and set a flag on the in the command struct. So when you run a command with an ampersand at the end, with the background command, your shell should not wait for it to terminate. Instead, it will need to maintain a list, which could be a global array, of all the background commands. If it's a global array, as opposed to something like a vector, that means it has a limited size that should be described in the limitation section of your documentation. And you should print the job number of the background command, which is just the index into the list. Job number 0, job number 1, and so on. If you are doing the bonus, in order to tell us that you're doing a bonus, when I run your shell without arguments, so reading input from standard in, it should print the message enable background command support as the very first thing that it does. If it does that, then we know to test out your background commands to see whether you get the bonus. If you don't do this, then there's a very good chance we won't realize that you implemented background commands and you won't get the bonus points for it. Notice you should not print that message when you're taking input from a script file, because that would cause many of the test cases to fail. This is purely in interactive mode. The other commands that the other things you will need to implement besides background commands, so that background command just means don't wait, but we need to be able to do a few things. Jobs will list all of the background commands. Well, we have the number, that's just the index into that array we're talking about. The process ID, well, you got that when you did fork. So even though you didn't wait on the process, you need to do something about it. So you can add the command. So in that list I was mentioning, you can add both the command and the PID. So you could have an array of struct command pointers and another array of process IDs. Now that does make things a little tricky, because when you run command in the background, it's running in the background. So you can't just free its command structure immediately if you're putting it into this array. Instead, you'll need to make sure that you free it when you take it out of the array, but that you also free the command structure if you do wait on an external command. Foreground FG command should bring, you give it a number and it will do wait PID on the process ID associated with that job number. Just like the wait PID in the parent or in the parent process for normal external commands, you should ignore interrupt signals and then re-enable those. You should print a message if the exit status is non-zero or terminates. So FG really is doing the wait and all the related stuff that you didn't do in when running the background command. Just you're postponing that for later. If you call FG without providing a number, it should work on the most recently started job that's still running. So in this case, if I have these two jobs, if I do FG without any arguments, it should wait for process 12373. So again, there are more hints here. The bonus is worth 15 points, but make sure you have a completely functioning implementation of everything else before starting on the bonus. Also, I would recommend before you start on the bonus, upload your completely working implementation of everything else. That way, if you don't end up getting it working or you've got errors in your program, remember we will still be applying these grading criteria. So if you implemented the bonus, but that caused you to have a warning, you've lost those 15 points that you gained. I recommend having your solution without the bonus already uploaded, and then you can do the bonus, and once you get it working, upload it as a replacement. We'll grade the latest submission that you make. Um, note that late penalties still apply to the bonus, although I'm likely to be making an announcement about late penalties very shortly. Okay, so those are the specifications. In the next video, I will talk briefly about how to get started with the program. Thanks.